Now we would like to discuss Pharma MacBeth cross-sectional regressions. So first of all, you might wonder why do we actually need this kind of approach. So let's consider a universe where we have n assets, and t is the time dimension. So for instance, in new cryptocurrency markets, we have about, let's say, 5,000 cryptocurrencies, but we have only, let's say, 5 years of monthly observations. So in this case, n, which is the cross-sectional number of assets, is much larger than our time dimension. So when this is the case, so it follows that we cannot do any seemingly unrelated regression analysis, because simply if we would like to test, for instance, if Bitcoin would price all of our 5,000 cryptocurrencies, we cannot run this model here since we have less than 5,000 time series observations, so we don't have enough degrees of freedom for estimating our parameters. So whenever this is the case, and this is just one example for why it could make sense. So another example why or when we can use Fama MacBeth cross-sectional regressions is, for instance, if we want to investigate hedge funds, and we want to investigate which risk factors price hedge funds, for instance. So, and we have only limited data in the time dimension. For instance, for some hedge funds, we have data available for the let's say, if this is the timeline, so we have data available for here, for the beginning of the sample, but then this hedge fund disappears, and some other hedge fund is launched much later in time, so we have only data available from here. So, but anyways, if this is the constellation that we meet, for this hedge fund here, we can estimate a beta, or the beta loadings against the risk factors, given this time period, let's say, I don't know, 50 months, 60 months. And for another hedge fund, we can estimate the corresponding beta for the same risk factors, but a later time. We use just these observations here in order to estimate the beta. But the main thing is that we get our betas for all of our assets, and that we have some time window where we can estimate the corresponding betas. So that's basically one idea, or one other circumstance when it makes sense to use or to investigate the asset pricing implications using Pharma MacBeth cross-sectional regressions instead of our seemingly unrelated regression framework, where we simply need a long time span of data, and the data must be available, the same time span must be available for all of our assets. So there are reasons for why this methodology has been developed, and it's actually a paper from 1973, if I remember correctly, where this approach has been proposed from Pharma and MacBeth, of course. So how do we proceed now? This is obviously something that standard econometric or statistical software such as eViews doesn't offer, so we have to code it by ourselves. And we remember, some of you might have participated in the RFM course, Research in Financial Markets, and there we already discussed one possibility how to implement Pharma MacBeth regressions. So there are many different possibilities how you can implement Pharma MacBeth regressions. You can start with the cross-section and then you go to the time series dimension, or you can do the other way around. You start with the time series regressions and then go to the cross-sectional regressions. So there are many different methodologies how to implement this approach, and it has been refined and refined over and over again. You can imagine. And in this course, we will only discuss a very simple methodology or type of Fama MacBeth regressions. And of course, this approach has some drawbacks. Yeah, and in the planned course for next year, so the follow-up course of this course here, what we will do then is hopefully, at least I have planned that we go through a more sophisticated type of Fama MacBeth regressions, where we basically construct synthetic samples, yeah, bootstrapping, and where we, based upon this synthetic samples, we get our risk premium estimates, yeah, which might have much better statistical properties, yeah? But we have to start somewhere, obviously, so we need to get the fundamentals straight. So Fama MacBeth. So this is again like similarly unrelated regression techniques, so we operate with multiple equations, obviously. Yeah? And in this case, the dimension, so the cross-sectional dimension, can be larger than the time series dimension, yeah? Which is forbidden, obviously, in time series approach. In time series, it must be true that we have more time series observations than we have assets. Yeah? So now we are here, n may be larger than t. Of course, in the example that we go through, obviously we have always that the n is smaller than t, but in practice it can be larger than t. So let's start with the time series. Yeah? We start with the time series. So the first step is, okay, let's consider our time series models. So let's start with y, like usual in this course. So y are the excess returns of asset 1 at time t, is equal with alpha 1 again. Yeah? Then we have here a beta 1, 1, which is the sensitivity of the first asset against the first risk factor x1t. And moreover, we have beta 1, 2 x2t, which is the sensitivity of the first asset against the second risk factor, beta 1, 2 times x2t, plus epsilon, which is again our error term, yeah? Which is usually assumed to be normally distributed, yeah? With so E1t assumed to be normally distributed with zero mean and sigma 1 square variance. Okay, that's standard assumption, but we know already that practically this is often violated. When not always. So we have a second equation, we have a second asset here, asset 2, y2t, yeah, is equal with alpha 2, we have again an intercept term, we allow for an intercept term, plus beta 2, 1, which is the sensitivity of the second asset against the first risk factor, x1t, plus beta 2, 2, which is the sensitivity of our second asset against the second risk factor, x2t, plus again an error term, epsilon 2t. And again, same assumption, normally distributed with mean 0 and variance sigma 2 squared. Yeah, so, and we have n assets in our universe, so finally we end up with ynt, which is equal with alpha n plus beta n, 1 times x1t, yeah, with the sensitivity of our nth asset against the first risk factor, plus beta n2 times x to t plus our error term epsilon n t. So, and here in between we have all of our n acids captured. So this is a system of n, capital N equations. So the first thing that we recognize here, obviously we have here a two risk factor model. We have two independent variables, or risk factors in our context, which is x1, this guy here, which is the same across all equations, and x2, which is also the same across all equations. So it's a two risk factor model. And moreover, we have the same setup. Basically, we have always intercept term in our equation, in our time series equations as well. So what we do is now, equation by equation, we estimate via OLS, our famous popular formula, B hat 1, which is the parameter vector capturing alpha 1, beta 1, 1, beta 1, 2, which is the corresponding parameters for the first equation here, and we denote it as B hat 1. We estimate it via OLS by x transposed x inverted x transposed y1. So we define our X matrix again, which we know already, which has ones in the first column, then the vector, corresponding vector of risk factor of x1, excess returns here in the second column, and in the third column we have the excess returns of our second risk factor, or here denoted as x2, and so on. So it's a t by 3 matrix, obviously. And our y1 is the vector of a t by 1 vector of excess returns from our first asset, here denoted as y1. So we define our matrices, we run our OLS model, and what we get is the parameter vector b1 hat, which is a 3 by 1 vector, which gives us in the first array the estimate of the alpha hat 1. In the second array we have the estimate of the beta hat 1, 1, and in the third array we have the estimate of the beta hat 1, 2. We do the same for all equations. So we always run OLS here as well, and getting our b hat 2. Again, we do the same thing. We do it by OLS, x transposed x inverted, x transposed. Now we take y2, we multiply x transposed x inverted, x transposed with the excess return vector of our second asset, and what we get is then the corresponding parameter vector giving us the estimates for alpha hat 2, beta hat 2, 1, beta hat 2, 2, and we do it for all the equations, and finally in the last equation we get the corresponding estimates denoted as b n hat, and this is given by x transposed x inverted x transposed y n. So we do it iteratively for all equations separately. So obviously what we get then, so we get via OLS parameter vectors alpha 1, so the alpha 1 hat, then we get beta hat 1, 1, beta hat 1, 2, we get the alpha hat 2 for the second equation, beta hat 2, 1, and beta hat 2, 2, right? These guys. And so on and for the last equation we get then our alpha n, beta hat n1, beta hat n2. And of course these vectors here would be longer if we have more risk factors, obviously. Yeah? It's straightforward. So what we do now is, we grab the point estimates. We don't need the alpha, because we are not interested in the alpha hat in our cross-sectional approach. The question is that we ask, how does the variation of the betas, does it explain the average returns of our asset? That's basically the question that cross-sectional Pharma MacBeth regressions address. So does the variation of betas explain the variation in expected returns? And expected returns, we talk about sample averages of our assets. That's the question. And of course we can also perform asset pricing tests in our cross-sectional framework, but this is what we will talk about then very soon. So first of all, what we do is we, having our point estimates, we grab for all of our vectors, we grab always the corresponding element for the first risk factor and put it into a matrix we denote it as, let's denote it as capital B hat. Capital B hat, so the first element would be then this beta hat 1, 1, so this guy. The second element would be